All right, so the title of this module is Animation, how to do animation for some dynamical problems. So let me start with some very simple example how to animate the motion of a projectile. So in your dynamics class, you've solved many problems on the motion of the object thrown under the influence of the gravity. And I'll just show you a very simple example of how to animate the motion. So, but let me just give you a very brief background on this. Projectile motion. So projectile motion looks like a parabola, right? So if you throw this from some initial altitude at the velocity initial velocity v0 at an angle theta, then skipping all the physics and math, let me just show you that x of t, the displacement in the horizontal axis is going to be given as follows, and the displacement on the vertical axis is given as follows. Okay, and you can also compute time in air, which is going to be given as follows. Okay, all this could be done. You probably already did this as part of your dynamics class. Okay, but this is all the background that I want to give you as far as this goes. So how to do the animation for this? Okay, so projectile motion. So you introduce all the data that you're given, such as v0, y0. For some reason I call it x0 here. Why don't we call it y0? And then y0. Okay, introduce time in air, which is just the formula that I gave you. And let's identify the trajectory of my point mass. So I define the vector of the time. So it's going to be from 0 to the value t star, which is the time in the air. So I call it time in air, with the step size of 0.05. Okay, and then I define the for loop, and basically for each value of time, I'm going to define the x position and y position. And xy is going to be the position of the point mass in air at each instant of time. So once I get out of this for loop, once I get out of this for loop, I will have for each value of time, I'm going to have the values of x, which is the displacement in the horizontal direction, and y, which is the displacement in the y direction. It's going to be all packed in vectors x and y. Okay, and then you're going to plot this. Okay, so you plot x, y, and also you plot x, y, meaning that MATLAB will plot the entire path for you. And then you also plot x sub I and y sub I, which is the position at every time sample. And I'm going to mark that position with the star. Okay. Next, so MATLAB will plot this. And then my next command is called get frame. So I'm going to define that frame as m sub I. So MATLAB will remember that frame, that basically it's a snapshot. It's a picture of that current plot. And then it's going to go to another loop. So I'm defining a for loop which runs from 1 to the length of the t vector, which is from 0 to the time in air, with the step of 0.05. So for each basically sample time, I'm going to take a picture of the motion. And then once I get out of this for loop, I'm going to show myself a movie through the command called movie. And then that's going to be the vector m, which collects all the frames taken at each time sample, which run from 0 to the time in air with the step of 0.05 seconds. Okay, so let me show you what it looks like. Hmm? Okay. Okay. So hopefully you can see it. So this is the path of my projectile. Okay. All right. So let me show you maybe a bit more involved procedure. So let's say, so here in this previous example, I knew the path of my object. So I knew x of t and I knew y of t as a closed form expression. So my x of t was v0 times t cosine theta. My y of t was minus gt squared over 2 and so on. Sometimes it's not possible. Sometimes you get this x of t and y of t as an outcome of the integration of some differential equation. So how to handle this? So in this case, I'm going to show you the integration of the pendulum motion. In the previous modules, what we've done is we've shown you how to integrate differential equation through the ODE command and state space representation. So I'm going to capitalize on this. So if you remember, actually, let me show you some background on this. So the background goes as follows. So the pendulum equation. Obviously, I'm going to skip all the derivation of these equations, but just to give you what the equation looks like. Okay, so equation looks like theta double dot plus g over L sine theta is equal to 0. Okay, state space representation. Looks like this. So you first introduce the first state variable x1, which is theta, x2, which is theta dot, and then you rewrite this equation in the form of a state through the state variable. So x1 dot is going to be theta dot is going to be equal to x2, and x2 dot is going to be theta double dot. From the equation, you get that it is equal to minus g over L times sine theta, which is x1. Okay, so this is state space representation. This is what MATLAB understands. So you need to, if you want to integrate some higher order differential equation or any kind of differential equation, even first order, you need to bring it to the state space form. Okay, so let's do that. So what we're going to do is we're going to first integrate this differential equation so that we can get the values of theta as a function of time. Okay, so we introduce all our constants. G is 9.81. Let's say the length of the pendulum is 1 meter. The radius of the ball is 0.05. I need the radius of the ball so that I can do the animation. My initial conditions, since my state space representation involves two parameters, x1, which is the position, theta, and x2, which is theta dot, which is the angular velocity, I need to introduce both. So let's say I start with the angle of pi over 3, 60 degrees, with 0 initial velocity. Okay, my t-span is going to be from 0 to 20 seconds with the step of 0.02. And this command basically integrates this differential equation. We've done this, I'm not going to explain how MATLAB does it, but we've done this before, but it communicates with the subroutine called RHS. It's right here at the bottom, which defines the right-hand side. Okay, it goes back and forth at each step of integration, and when it's done, basically MATLAB knows the values of the state variables, x1 and x2. In our language, it is theta and theta dot. So MATLAB knows both of them. How do we do the animation? So we define the for loop that runs from 1 to, the index of that for loop is going to run from 1 to the length of the time vector, t. I'm going to define my axis, it's better for the animation. It's better to define the axis, because otherwise MATLAB is going to at each step of animation is going to adjust axis, and it's just not going to look right. So it's better to fix the axis, the range of axis. Since I kind of know what the range of motion is going to be, because I know that it's going to go from minus pi over 3 to pi over 3, so I kind of know what my range of axis should be. So here I define, so I need to define, basically in order to do the animation for this simple system such as pendulum, I need to define the line and I need to define the ball. Okay, so this Lx is going to define the position of the end point of the ball, and I'm going to draw the line between these 2 points, Lx and Ly. So Lx and Ly define x positions of the ends of the bar, and Ly defines the y positions of the ends of the bar. Okay, and I'm going to connect them through the command called line. So line connects the two ends of the rod of the bar. And then you can add the bells and whistles here. So my line width is going to be equal to 3. Okay, you can define this line width. In order to define the ball, you invoke the command called rectangle. So it's a very general command. It can rectangle can draw a rectangle. It can draw a rectangle with rounded corners. It can draw ellipse. It can draw a ball. Okay. If you need to know more about it, you can always type help rectangle, and MATLAB will explain you how to plot this. But basically, you indicate the rectangle. First, you're going to position that ball where that ball is going to be. So you're going to start at this point. So let me go back into here and explain you how MATLAB does this. So I have this line. I define the coordinates of this end points of this line, this and this. And then I have a ball at the very end here. So I'm going to start drawing this ball from this point. Okay, so MATLAB is going to draw this ball, this ball from this point. I have to define the coordinates of this point. And that's what I do here. So you need to geometrically figure out where that point is and indicate the coordinates of this point. So those are going to be the coordinates of this point. Then you have to define the curvature. Again, you can see the details in the MATLAB description of the command rectangle. But if you indicate under the curvature, if you indicate 1, 1, that means that the expansion on x and y axis is the same, which means that you're dealing with the ball. If it's different, if it's 1, 2 or 3, 1, it's going to be an ellipse, either expanding in x direction or y direction. But 1, 1 is the ball, and you can actually give the color. It's done by the string called face color. And let's say I would like my ball to be red. Okay, the default color for MATLAB is blue. So my line, my bar is going to be blue, and my ball is going to be red. So at each step of the way, I'm going to, so I've drawn this line and I've drawn this rectangle at each step of integration, at each time step, and MATLAB will plot this on the figure, but I would like to capture that frame. So I'm invoking the same command called getFrame. So basically MATLAB will memorize this. I'm defining this as m sub I. And then I have to clear the frame, okay, clear this figure, because otherwise MATLAB will superimpose, and then you will just see the picture, the positions of the pendulum at each instant of time. You don't want that. So you capture this frame and then you clear this. You capture this frame and then you clear this. And then at the end, once you get out of this loop, you just play the movie, and in the brackets you define this vector m, which contains all the frames that you have collected. So let's see. It's going to look like this. Okay, and that completes this module.